designing a wind anemometer. So first things first, we need to design the circuit so that we can read the rotations on an anemometer, which basically kind of looks like this. Is basically an anemometer device. We have the wind blowing and then this rotating around the shaft. And so the way we can design it is we know the fixed diameter of the shaft. So let's say we use PVC pipe like I have at home. We know the diameter, therefore we know the radius. Then what we do is we mount a magnet to the shaft. The magnet's going to be tiny. Then what we do, let's blow this up a little bit. We take that magnet, we sort of embed it into the wall of the pipe so that it doesn't add to the diameter. And what this is going to do is this is going to rotate around freely based on the wind pushing the device in one direction or another. And then what's going to happen is we place a Hall effect sensor. A Hall effect sensor is basically a fancy transistor that turns on and gives a pulse every time it senses a magnetic field. One side of it goes to VCC, another side of it goes to ground, and the third side is the output signal. This is going to give us a waveform that looks like this, basically a square wave. Once we have a square wave, we can invert this to determine to get a rising edge kind of pulse. And what we can also do is put it through a differentiator circuit, which is basically a capacitor, then a resistor to ground from the primary signal, which will be coming from the output. And this will give us something that looks like this. So it'll really detect an edge. We could put a diode facing backwards onto the circuit, which will, with the diode, make it look something like this, which will really narrow the pulses, make them easy to count. Okay, once we have this, then what we can do with this signal, that's the output signal, we can make this, add this to a counter chip. CD4017, which is a decade counter. It counts up to 10. And what we can do with that is that information is we could actually cascade several of them together in case it rotates really fast, but I don't think it's going to be rotating that fast. But let's just say, for the sake of argument, we want to measure a potentially high speed wind. So we can cascade these together, where the carry out goes into the clock of the second chip, and the first chip clock is this signal right here. And this will give us an RPS, rotations per second. Okay, now what do we do with this information? So with this information, we need to be able to go from this value to, since we are in the United States here, miles per hour. So simplest way of doing that is basically math. If you had a microcontroller, this value goes into a microcontroller, you do some code, and you do the math in the code, and that spits out a value in the output. But I want to do this without a microcontroller. I want to do this all analog. So microcontrollers don't work well out in the ocean, near the ocean. The salt in the air will corrode them very quickly. So we need an analog type of circuit that's going to do this. So the way to do that is we can convert to RPM, which is just RPS times 60. And with that value, we can ultimately convert to miles per hour. So the formula, miles per hour, is known. It's basically 72 times pi times the radius over 965.6064, and all this times RPM, which is RPS times 60. So the formula is 72 times pi times radius times 60 times the RPS value, which we get from the counters here, over 965.6064. So from this value, we're going to get a frequency in hertz, which is rotations per second. And so this is equivalent to the frequency in hertz. Then what we do is we take the we're going to need to create a frequency multiplier here in order to find this. So let's say, for the sake of argument, that our shaft here is 1 inch in diameter. So if that's the case, then this formula becomes 72 times 3.14 times the radius, which is half of 1 inch, which is 0.5, times 60, all divided by 965.6064. And let's do the math on this. And the math on this is, let's see, let's get that going here. 72 times 3.14 times 0.5 times 60 equals, divide all that by 965.6064. And that gives us 7.02, which is basically equivalent to 7. So, and this is pretty simple. So 7.02, which is basically 7. So all we have to do is get the value of frequency here and put it through a frequency multiplier circuit. And the frequency multiplier circuit, all we have to do is just multiply it by 7, which is fairly straightforward, fairly easy. So frequency multiplier, now to get this value, is we have to put this RPS signal, which is coming out of these counters, the output, and what we do with that is we basically put it through a phase locked loop, or otherwise known as a PLL. So PLL is a circuit that basically it takes two signals and well, one signal really, and you can either divide it or multiply it, and it's a frequency signal. So let's say they create, there's a an IC, an integrated circuit that does that, and that is the CD4046. And basically what this does, if you want to draw a block diagram of this, is basically there's an input signal which is coming from here, and that input signal goes through what we call a phase detector. Well, it determines whether whether a wave is in phase with another wave. That's a frequency wave. So they could be of different frequencies. What that does is once it detects the phase, then it puts it through, well, it puts it through a low pass filter just to get rid of any signal noise. Then it puts it through into a voltage controlled oscillator. That voltage controlled oscillator then oscillates based on the input frequency, and that it becomes the output signal. But the beauty of this circuit is there is a feedback loop here, and this feedback loop provides this input signal with any changes that occur in the signal throughout, and will adjust the output frequency accordingly. So this CD4046 will be, if left alone, the input here is going to equal the output completely. So what we're going to do is we're going to put within the feedback loop a voltage, not a voltage, I'm sorry, a frequency divider. I don't know if this can be seen. So we're going to divide it by 7. divide by 7. When this feedback loop is divided by 7, this output, when it's combined with this feedback loop, gives you a frequency multiplier of 7. So it multiplies whatever input signal there is by 7. So whatever frequency we get in the RPS after we put it through this, we will get a readout that's miles per hour after we multiply that frequency, whatever frequency this is, by 7. It will be miles per hour. So how do we do this? Well, this is basically, there is a pin on this, which is, there's an input pin, there's an output pin, and then there's a VCO out pin. So this is VCO out, and this is VCO in. And so what we do with this is we bring this to another counter chip, and we have it count to 7. And after it gets to 7, which will be CD4017, once it gets to 7, after the output gets to the 7th pin, or the 7th output, then we're going to feed that back to this to reset. And we're going to trigger, and we're going to also feed the output of this into here. And that'll effectively give us a divide by 7 in our feedback loop. So for this entire process, we'll need a Hall effect sensor, 2 counter chips, a phase locked loop IC, and we need another CD4017, so 3 counter chips. Now, how do we display all this without a microcontroller or anything else? So this output signal that we get from here after the frequency multiplication of 7 will be our miles per hour value. And so what we do with this value is we're going to put it through a CD4026. We'll probably use 2 of them so we can get double digits. So CD4026 is basically another type of counter. But not only is it a type of counter, it's a decade counter, but it doubles as a driver of a 7-segment display. So those things on your clock radios, you know, that have the digital values that are 7 segments. I'm just writing random numbers here, but it looks kind of like this. This is the way you write a 27, for instance. And so this will directly drive these 7-segment displays, and whatever appears on the 7-segment display after all of this is going to be miles per hour.
Hey.
Yo. So all in all, we're going to need 1, 2, 3 CD4017s, times 3. We're going to need CD 4026 times 2. We're going to need CD 4046, which is the PLL, the phase locked loop, for frequency multiplication times 1, and 2 7 segment displays, and a shaft with the attached cups of 1-inch diameter. Oh, and the Hall effect sensor. That's fairly straightforward. So that's the design. If anybody sees this and finds a problem with it, then let me know. And, hopefully I can get this built relatively soon. We'll make it happen. Thanks for watching.